Hello dear students, welcome to my second class on module 2 properties of integers. In my previous lecture video, we discussed about mathematical induction, problems based on the mathematical induction. So in this class also, we'll be learning a few more problems based on the mathematical induction. Problem number 3, prove that for every positive integer n is greater than or equal to 24 can be represented as a sum of 5s and or 7s. Okay, so in the basic step, I need to represent 24 as a sum of 7 as well as 5, and in the induction step, I must assume s of k is true for k is greater than or equal to 24, and I want to prove this for k plus 1. Okay, so in the basic step, I am taking 24 as a sum of 2 7s and 2 5. That is 7 plus 7 plus 5 plus 5. So it is obviously true. So to prove this this s of 24 is true, I am using 2 7s, 2 5. So to prove that this 24 is true, I must have always 2 7s and 2 5. It is a mandatory one now. Okay. So now in the induction step, we assume that s of n is true for n is equal to k. So where k is a greater than or equal to 24. Then k can be represented as 7 plus 7 plus so on plus 5 plus 5 and so on. So I am taking this as r number of 7s and this one as s number of 5. So to prove that s of k is true, I must have r number of 7s and s number of 5s. And one thing, note that here this r must be greater than or equal to 2 and s must be greater than or equal to 2. Because to prove that s of 24 is true, I must have 2 7s and 2 5s here. So now, the next thing is what? I want to represent k plus 1 is true now. So here k is there. So for k I am writing like 7 plus 7 plus 7 and so on. 5 plus 5 plus 5 and so on. So now I am going to prove the statement is true for k plus 1. To prove k plus 1, I am going to add plus 1 on both the sides. So after adding plus 1, I will be getting what? K plus 1 is equal to 7 plus 7 plus so on for r times 5 plus 5 plus 5 for s times plus 1, since I am adding 1 on the both the sides here. So now from this 7s, I am taking 2 7s outside. So I will be getting what? These 7s are there for r minus 2 times now. So I will be getting 7 plus 7 plus for r minus 2 times, since I am taking 2 7s outside. That is 7 plus 7 I am taking separately here. Plus 5 plus 5 plus so on by s. This is for s times plus 1. So by combining this 7 plus 7 plus 1, I will be getting 15. So this 15 can be divided into 5 plus 5 plus 5. So I can combine with this s number of times with 5. So I will be getting what? 7 plus 7 for r minus 2 times plus 5 plus 5 plus for s plus 3 times. Since I am adding this 15 with this 5 series, like 5 plus 5 plus 5, I can add it. So I am adding plus 3 extra terms here. I will be getting s plus 3. So same thing here also, k plus 1 also I am getting like all 7s for r minus 2 times and all 5s for s plus 3 times. So it shows that k plus 1 is also a sum of 7s as well as 5. So hence I can conclude that s of k plus 1 is true here. So now problem number 4. Prove by mathematical induction that for all the positive integers n is greater than 1. The sequence is given like 1 into 2 plus 2 into 3 plus 3 into 4 plus so on plus n into n plus 1 is equal to 1 by 3 into n plus 1 n plus 2. So same thing here also, we have to prove this one by 2 steps. One is basic step, one more is induction step. So the first thing is I must take the statement s of n. So s of n will be equal to what? 1 into 2 plus 2 into 3 plus 3 into 4 plus so on plus n into n plus 1 is equal to 1 by 3 into n plus 1 n plus 2. For all integers n is greater than or equal to 1. So basic step. So in the basic step, I must prove the statement is true for s of 1. I mean for n is equal to 1 in the above statement. So here if n is equal to 1, if I replace, I'll be getting what? 1 into 1 plus 1. 1 into 2 I will be getting. 1 into 2 will be equal to 1 by 3, 1 plus 1, 1 plus 2. I'll be getting what? 1 into 2 is equal to 1 by 3 into 1, 1 plus 1 into 2 plus 1. After simplifying this, so this 3 gets cancelled, I'll be getting 1 into 2 will be equal to 1 into 2. So it is a true statement, right? So which is clearly true. So I can conclude like the statement S of n is verified for n is equal to 1 here. So induction step, we assume that the statement S of n is true for n is equal to k, where k is an integer which must be greater than or equal to 1. So that is, we assume that the following statement is true now. So S of k will be equal to what now? 1 into 2 plus 2 into 3 plus 3 into 4 plus etc plus k into k plus 1 will be equal to 1 by 3 k plus 1 k plus 2. So now I must prove that S of k plus 1 is true. So to prove S of k plus 1 is true, I am just converting k as k plus 1, right? So k is equal to k plus 1 means I am going to add few terms now. How to add means, since here k into k plus 1 is there, so to convert the equation as S of k plus 1, I must add k plus 1, k plus 2 on both the sides. Okay. So by adding k plus 1, k plus 2 on both sides of the above equation, I will be getting what? S of k is equal to 1 into 2 plus 2 into 3 plus 3 into 4 plus etc so on plus k into k plus 1 plus k plus 1 into k plus 2. Okay. So adding both the sides k plus 1 into k plus 2, I'll be getting what? 1 by 3 into k plus 1 k plus 2 plus k plus 1 into k plus 2 I'm getting here. So I can take k plus 1 k plus 2 common factor. I'll be getting what? 1 by 3 k into k plus 1. So taking LCM, I'll be getting 1 by 3 into k plus 1 k plus 2 k plus 3. So for the S of k equation, I'm having the equation like 1 by 3 k plus 1 k plus 2. For S of k plus 1, I must have what? 1 by 3 k plus 1 k plus 2 k plus 3. So same thing I got here, right? So hence I can conclude that S of k plus 1 is true. Therefore, on the basis of the assumption that S of n is true for n is equal to k, which is greater than or equal to 1. So the truthness of S of n for n is equal to k plus 1 is established here. One more example, prove by mathematical induction that 1 square plus 3 square plus 5 square and so on plus 2n minus 1 whole square is equal to n into 2n minus 1 2n plus 1 by 3 for all integers n is greater than or equal to 1. So same thing here also. So the first thing is we have to prove the statement by using the induction step. So first assume S of n. So S of n will be equal to what? This statement. The given statement, that is 1 square plus 3 square plus 5 square plus so on plus 2n minus 1 whole square is equal to n into 2n minus 1 2n plus 1 by 3. Okay. So now I am going to prove the basic step. In the basic step, I am going to prove the statement S of n is true for n is equal to 1. Okay. So I will be getting what? 1 square is equal to 1 by 3 into 1, 2 minus 1 into 2 plus 1. So after simplifying this, I will be getting 1 is equal to 1, which is clearly true statement. So S of n is true for n is equal to 1 here. So next is induction step. So in the induction step, I am going to assume the statement S of n is true for n is equal to k. So where k is an integer which is greater than or equal to 1, that is, we assume that the following statement is true. That is, S of k is equal to 1 square plus 3 square plus 5 square plus so on plus 2k minus 1 whole square is equal to k into 2k minus 1 2k plus 1 by 3. So since here 2k minus 1 whole square is there for S of k, for S of k plus 1, I must have 2 times of k plus 1 minus 1 whole square. It will be equal to 2k plus 1 whole square I will be getting. So 2k plus 1 whole square means I must have 2k plus 1 whole square on both sides of this equation. Okay. So I will be getting what now? S of k is equal to 1 square plus 3 square plus 5 square plus so on plus 2k minus 1 whole square plus 2k plus 1 whole square is equal to k 2k minus 1 2k plus 1 by 3 plus 2k plus 1 whole square. So now I can take 2k plus 1 common factor, remaining will be k into 2k minus 1 by 3 plus 2k plus 1. On simplifying this, I will be getting what? 1 by 3 into 2k plus 1, k times of 2k minus 1 plus 3 into 2k plus 1. So expanding this, I will be getting 1 by 3 2k plus 1 2k square minus k plus 6k plus 3 by expanding this. Then on further simplification, I will be getting 1 by 3 into 2k plus 1 2k square plus 5k plus 3. On expanding this by using factorization, I'll be getting what? 1 by 3 into 2k plus 1, k plus 2, k 2k plus 3. Okay. So to prove that this statement is true, like for s of k plus 1, I must have actually what? K plus 1. So here k plus 1 I'll be getting 2k plus 1. Here 2k plus 3 I must have, right? So then same thing I got here. 1 by 3, 2k plus 1, k plus 2, 2k plus 3. So hence I can say that the statement s of k plus 1 is true. So on the basis of this assumption that s of n is true for n is equal to k, which is greater than or equal to 1. So hence the truthness of s of n for n is equal to k plus 1 is established here. Thank you.